Thank you for the introduction, Kento. I will jump directly into the topic. The presentation as it appears on the slide or in the program is ongoing collaboration research with Europe. Now you have two options. We stick to the program, original plan, which is updating on the ongoing collab project, which it's interesting to know what's ongoing, especially with a very close partner in EU, HANAMI. Or we could go to a different topic, divergence between AI and HPC. I don't want to take the blame myself because Kengo Nakajima-san will not be very happy if I diverge, so I will let it out for a vote. So please, this is just to motivate you into the vote. So those who prefer the original topic, please raise your hand. Those who prefer the other topic, raise your hand. Okay, I guess it's a democratic vote. Yeah, I know, but to be also fair, I'll just explain also what's HANAMI in 1 minute so that I also cover the main topic. So HANAMI is a project that is between EU and Japan. There's a lot of alignment and historical collaboration between Japan and EU. This is not the first one. And the point is that to push forward what we had for digital partnership into more HPC, it's very focused on HPC. And it has those core areas, which is climate modeling, material science, biomedical. But of course, it looks into HPC infrastructure and artificial intelligence. A lot of partners from Japan and Europe. It's well balanced. The firepower is well balanced, if you may say, but the funding was a little weird. It's kind of asymmetric. HANAMI being funded by EU, and in Japan there is no corresponding funding. But that, nonetheless, didn't stop things. There's a lot of decent progress there. The project started in 2024, 3 years to go, with a lot of activities. And this is where probably I should cut off and move to the other slide. But I would be very glad to talk more about HANAMI outside. And that was HANAMI in a nutshell. So this is where I switch. And apologies again. I know people don't like disruptions in programs. So this talks a little bit about convergence and divergence of AI and HPC. There is a central message, which is, again, as you see, it's based a lot on personal opinion and speculation. It's not 100% facts. So if you think this is wrong, you might be right, I might be wrong. Money will go after AI. Market will mostly spec for AI. That's pretty clear. HPC has no option but to shop in that market. There's a wiggle room. You can try to maneuver around, but at the end of the day, we are a small market and we have to shop there. And there is divergence, or the question is basically what this slide is asking. Is there more divergence that we might want to like to think? Okay, so just to clarify, when I say HPC, because HPC means different things from different people, I mean large-scale scientific computing. This is the first assumption. Second assumption, let's say for the time being, there's no violent bursting of the bubble of AI. There's a bubble, even AI people acknowledge that. And if it bursts, it might be a very different scenario. We might be buying DGXs for $100 each. I don't know. But if it doesn't, let's say it's a slow deflation, or let's say the bubble is more contained, like the dot-com bubble, which I doubt, given many sectors now are being pulled into the bubble, not just compute, like energy, power, and so on. Or let's say it gets cheap enough, or they iterate over it to the point that it can impact through across many fine-grained market to the point that there's a huge market for it. But let's assume there isn't violent bursting. And things for the next 5 years, for example, will be as they are. And let's also make an assumption here that AI companies cannot do all of large-scale scientific computing because simply scientific computing will remain to be done by current institutions because they will not go out and hire 200,000 scientists in Meta or Google. They might try to penetrate in some areas, which makes money for them. But by large, most of science will remain to be done by scientists in their traditional institutions. And also, last assumption is, let's just say that HPC is a niche market. It has always been. That's a fact. And let's say it remains to be a niche market. So those are the assumptions I start from. So obviously there's too much analysis in AI and HPC. They're converging, two sides of the coin, they're aligned, which actually there's a lot of truth into that. A lot of truth, and that's correct. And you can always find ways where they're aligned. But we also must acknowledge if there are differences because if there's alignment, that's good for us. We just piggyback on them and we do HPC efficiency as we do and we try to live another day with any wave of hardware or changes. But divergence, the issue with divergence is very disruptive. That's probably, we should acknowledge how much of a divergence is it, and is it a show killer for us or is it not? There can be a lot of divergence that no way I can cover in 20 minutes. But I guess it touches across the entire spectrum from compute to memory to network storage to algorithms to programming to libraries. I'll just touch on each of them, and I'll prepare a longer version of that if you wish to discuss more than that, something in an hour or so we can do that. First, I'll jump to compute. The clear one is low precision, is pushing out higher precision. That's obvious for everyone, and I don't think it's going to change. Libraries, and I think this is again an opinion, every library that can use emulation will probably use emulation. And that's where everybody pushing in that direction. There's something funky. Yeah. So everything that can be emulated will be emulated, right? I guess so. And we can already see signs of that, where a lot of push is coming, including from this institute, R-CCS, hosting this symposium, to emulate, higher precision with lower precision, using a lot of schemes, numerical schemes like Ozaki scheme, and expanding that even into lower precision like int 8 and so on. And we'll see more of that. So probably people will just keep working on that. Some might argue, I'm not an expert on numerics, but some might argue this is not enough, it might not work. But people probably will push as much as they can to the end of it. For some libraries can survive. But what about general code? That's a problem actually, because a lot of HPC is not using libraries, or they partially use libraries, but there are also hotspots outside libraries. There's a mix of algorithm solutions out there, nothing new here. People have been doing that since 2010 or so. In a different context, when mixed precision meant FP64 and FP32. That's the context of mixed precision HPC before the AI craze came. And there have been solutions that are algorithmic. You just take your algorithm, rip it apart, and do it from scratch. Obviously, this is a problem because that means you need to do it with each algorithm, which is not tractable. It is just too much work. You can use some form of automated mixed precision, in which you assume you have some library or hardware or software that tries to figure out the precision, tracks error, and works. Mostly relying on automated differentiation methods, tracking the error as propagates. Unfortunately, historically, this had worked with smaller toy problem, but nothing large-scale production, because it also has issues with scaling. Plus, you cannot do a lot of it in runtime. So if I change my program or my settings or my input or whatever, I have to repeat that again. And there's user-assisted, which is something in the middle, right? But again, it's an emerging area. But the elephant in the room is none of these solutions are mature. So if you want to deploy any of these solutions with existing codes in the next 5 years, I think that's going to be hard. So what's the risk here? The risk is that inefficient emulation mixed precision can lead to small effective gain in performance with new systems. This is a very big risk. You would ask, well, not a big problem. Our code is memory-bound code anyway. We're in HPC. It's very rare that you use actually non-memory-bound code, right? Simple answer, you could say, yes, it benefits, because when you go with lower precision, you're reducing the memory traffic, which means you're getting more sustained, higher efficiency with accessing your memory. The complex answer is that low precision, as it exists now, mostly resides on matrix engine or some accelerated units. And there's lack of support for anything less than level 3 blasts for L1 or L2 blasts. This might change in the future, but it's an issue. And this is a study recently, Lenchi, here he has a paper under review, has worked on to show that the memory paths, the pathways going to this matrix engine and your typical memory on a GPU is the same. So you don't really gain any much of that. Plus, because the matrix engine units are not very malleable for you to use, so you have to do a lot of redundancy, for instance, and go along the diagonal, and then you lose you're just loading so much data to use some of it, then you're not getting anything. So it's an issue also for memory-bound codes. There's also the issue, since we're in divergence in compute and how rigid the specialized hardware is. There's all types of rigid specialized hardware. I think actually there was a whole talk from yesterday that talked a lot about specialized hardware. They take different forms. They can be specialized compute units added to CPUs and GPUs, like matrix engine, like tensor cores is one example. They can be ASICs, like a whole chip designed just to do that. While you think they're intended for AI market, actually there has been a lot of activity. We did a small survey, and you can find the URL here, tracking papers working on it. You will see, of course, the big chunk of papers trying to use matrix engine beyond AI are still on BLAST region, but maybe BLAST, but not for AI. But other than that, you're seeing a lot of activity. Algebraic multi-grid, FFT, stencils, and those are works published in very good conferences. So it seems there's a lot of activity. That being said, they're very rigid and very hard to program, very hard to squeeze performance out. So using basically tensor cores in NVIDIA is like using GPUs pre-CUDA when people do shaders and such. Maybe we need a CUDA moment for matrix engines to lower, raise the abstraction and make it more malleable, but at this stand it's not. So moving forward, it will be a very big challenge with all this compute to use. A little bit now on memory. So high bandwidth memory is a requirement in both HPC and AI, which is very good, and this is where we're aligned, right? And if anything, HBM actually appeared in GPUs, and then even in Fugaku 64FX, because you need this high bandwidth memory to drive your application, because a lot of application are memory bound. There's also on the side potential processing and memory innovation driven by AI. It would be very welcome in HPC if it happens, but we're good on bandwidths. But our versions comes in capacity actually. AI needs a lot of memory, and that's clear. Actually, arguably, you can argue that even the main reason people buy GPUs is for memory, might not be for compute. It's an opinion, I might be wrong. HPC, however, some applications that need memory, but not all of them. Need bandwidth, and of course, getting bandwidth by capacity is a very bad idea. A good example is just look at NVIDIA A100, the 80 gigabytes version, the 40 gigabyte version. You're getting 2 exa capacity, but only 1.25 exa bandwidth. So it's not very useful for us for bandwidths, right? Current algorithms do not benefit from more memory. If you give more memory and you still have your algorithm as it is, it's not really useful. So you might need, this is probably a solution, but I don't know if it's even tractable or not, to rewrite algorithms for abundant capacity in HPC, like excessive, extreme, aggressive lookup tables, or memoization, where you just compute something, leave it, and go back to it again, something like that. But as it stands, HPC doesn't look to be using a lot of memory compared to AI, and not all AI, not all HPC application. So the risk here is that we might end up as HPC having to pay much higher price for memory capacity we do not need. And it's very clear that the vendors will not make for us a version that has less memory on it, because again, we're a niche market, so they don't care about us. You have this bandwidth, this capacity in your GPU, and that's what you're gonna get. So which means low return on performance, because the memory is now a big factor of the price. HBM memory is really expensive. Next is network. There's a lot of ways to parallelize. Again, this was mentioned in previous talks. Depends on what you parallelize in AI. Like there can be forms of tensor and pipeline parallelism, which is both like model parallelism in a form. There's deep data parallelism, you just replicate the model. There's context or sequence parallelism, where you parallelize the input itself. And this is, for instance, from Llama 3.1 paper, where they did 4-tier parallelism within the node, tensor parallel, and outside the node. And there's a lot of work in that area. It's well understood. The TLDR version, or your short version, is that you sort them from the inner loop to the outer loop on ones that generate a lot of traffic, because that's where you will stay within the node and use multi-GPU. So in this case, tensor parallel pipelines, context, and data parallel, and they're probably best practice already in that domain because people have did a lot of work. There's a lot of performance models. This is well understood, I would say, at this stage. So scale up matters. Like AI favors local high connectivity. This is where a slightly, things diverge. So you can pick some topology. I'm not an expert, but there's many topologies that favor local connectivity. Scale out might be more niche, or it's important, but not primarily as important as scale up. And there's actually an evidence for that. This is not just an opinion. This is a fact now. Look at the H100 chip, which NVIDIA has a modified chip called H800. If you compare the features, and this is with a chip that's designed to be throttled in a way, to reduce the capability of the chip in AI workloads, clearly, right? If you look at at what they slowed down, it's nothing on the compute, actually. If you look at the tensor cores for 8 bits, 16 bits, it's the same. So why would you sell a chip that you wanted, to throttle or slow down AI workloads and not reduce the flops in the AI workloads? It's because this is actually the difference. If you want to sell H100 or H800, right? This is the difference in interconnect. That means the interconnect within the GPU server itself has to be 2 generations behind. If you're using NVLink 4, it has to be NVLink 2, right? So the throttling comes from the interconnect. It's a scale up. So the scale up is what throttles the chip. Chip doesn't is not itself throttled. Which is interesting insight to say that whoever looked into that and decided how do I constrain this chip but allow the company or vendor to sell it, you just constrain it this way. Another small note on the side that I found very interesting, relevant to us, the only other thing that's throttled is FP64 actually. So when people say AI is what matters, HPC doesn't matter. I think it matters to the point to whoever thought how to make this chip constrained for FP64, right? So it's not constrained on flops that are less than FP64, but constrained on FP64. But that's a side note, okay? So back to the original point, the scale up. So scale up does matter. I wouldn't say more than scale out, but it's much more or less emphasized in AI versus HPC. And there's a reason we did an analysis on that. This is so much numbers you don't have to look at, but if you just look at tensor parallel versus other modes, this is the amount of traffic in these red boxes generated, at each iteration basically, which is, terabytes generated of data. And this happens inside the node. So you try to stick these, most data traffic inducing mode of parallelism, which tensor parallel to be inside the node or expert parallel. And this is actually where you need scale up. There's effort, and of course, if you want to do alternatives, this is a slide or analysis from Jens Domke in R-CCS, in which you see, I will not go through it, but it says basically that you have to go through a lot of effort to be able to get squeeze out, scale out in HPC in an unusual way that we didn't have to do before. So, as I said, for AI, for network, the difference is, I guess, emphasize on scale up in AI versus HPC, which is a divergence point. Can HPC find a way to make it to its benefit? Maybe, but I don't know. Now, a little bit about storage. Storage, I guess, it's much less of a concern because this is where maybe we can align, but it will take some time. Because AI machine learning does have the four following features. It's mostly reading, so there is no very strong need for POSIX compliance because you're mostly reading data sets. If you're training, if you're doing inference, you're also mostly reading the output to generate your input. It's usually many small files versus very large files, like fewer large files in HPC, which drove the design choices for storage for a long time in HPC. It favors local storage versus surge storage because you can repeat the access to the data again and again and again if you're iterating over the data in epochs. It has different modalities maybe than HPC. And this is a study that was made, I think, in Oak Ridge on Summit Supercomputer. And as you can see, if you look to read at different sizes of systems, from flagship all the way to small, you can see that the read intensity is much, much more than the write intensity. And that's quite, and if you ask anyone who works in the field, they will tell you the same. The solution that is being adopted in that space area is just object storage, which simplifies things. And it looks like HPC is heading in this direction. I think Aurora has already an object storage system. So I think it's not a big divergence point, but it's something to keep in mind. Next is algorithms. I think this is a hard one. Apologies for the image. It looks low resolution. I don't know why. Anyway, when you have a hammer, everything is a nail. That applies everywhere, HPC and other than HPC outside. Dense linear algebra drives AI and machine learning. If you want to say, I will align, I don't want to diverge, I want to converge, then naturally you would say, then I take HPC algorithms and let's say matrixify. It make everything look like a matrix multiplication. That being said, this is, again, an opinion where I think it's not going to happen because it's not like we suddenly realize that computers are faster than linear algebra. Supercomputers have been favoring dense linear algebra since the 90s. It's literally how we benchmark systems, right? Systems have been designed for matrix multiplication and dense linear algebra for a very long time. That being said, we have not seen all of the solvers of HPC move to matrixify. Maybe it's complex, maybe it's not possible, maybe it's harder, maybe it's not tractable, maybe there's not enough human resources, but that has been the fact. And if you look actually into, this was a study we had in IPDPS in 21, we looked across very wide, sorry for the low quality, but I'll just describe it and you can take my word for it. What you see on the x-axis is a lot of applications, not just benchmarks. And what we looked at by profiling aggressively is to see how much blasts or gem or level 3 blast basically in these codes. And anything you see in purple and green, that's the amount of time going on gem or blast. Anything in yellow, it's not. This basically says there's not much going on with level 3 blasts in HPC codes. So it didn't change in the last 30 years, and I doubt people will suddenly change it now. Maybe I'm wrong. Next is programming, which is a big issue. Like we see the push for AI and AI space to use AI models to generate code or do If it doesn't generate, at least it does, code translation or code porting or support different backends, right? The holy grail, basically, of HPC. If you have used any of the nice LLM models, and if you have used or nobody that used it, it's very good for getting you code that works, especially if something is so again. But the issue that once you diverge into, once you go into a complex task, it stops working very good. And the worst part is HPC, by definition, you're always writing code for new hardware. New hardware means there's no code existing, means the model was not trained on it, right? So if you want to write code for some numerical algorithm or so that has been done 30 years ago, it's fine. If you wanted to write code on a hardware that you don't own yet, or it's just in the market, and for which there's no example code to train, then what would you do? It's out of distribution, then the model cannot figure out. And it really affects much. Just going from even the same vendor, from one GPU to the next GPU, or just say from the one CPU to the next CPU, right? You're immediately struck by how small difference in the design, cache line, or cache line size, or the cache hierarchy or something might affect your code dramatically, that you need to tune again for the next hardware. But if your model didn't see this data because nobody wrote the code yet, it didn't train on it, how would the model generate code for you that is reliable? So I think this is going to be tricky for HPC. In the space of enterprise and normal coding, you want to write some JavaScript or Python, something that this model has seen 100,000 times in data set, is perfect. But outside of that, for HPC, I doubt. Can help a little bit in HPC glue code, but the intense, the very critical kernels or so, I had much doubt. I would love to be wrong, because that means all of our lives would be easy, but that's basically at least how I see it. There are many approaches in machine learning, land, where you try to solve this problem. Unit testing, surrogate models, just evaluating the translation, round trip, which you generate the code and then go back again to see back if you can go back to source. You limit the machine learning to short sequence of instruction, determine transformations, symbolic execution, a lot of methods, but none of them actually guarantee you that the generated code works as it should intend, not to mention performance. We have, for the sake of time, I'll almost stop here. On some effort we're doing in that direction, that I will skip. So I guess I go back to the central message. Money will go after AI. Market will mostly spec for AI. HPC has no option but to shop there. There could be divergence. The question is this divergence big enough of a gap that it makes a problem for us? Because effectively, there are the following reasons you would want to use AI in science codes. You want to use it to be more efficient, to get higher fidelity in some solvers. What you're modeling is hard, so it can be easier in figuring out the mapping from input to output, because it's an inverse problem, you cannot work on it. Or tackling challenges that are intractable without AI. But here comes a question: what happens if the hardware you buy is for AI and the divergence is enough, especially on the precision part, that basically makes this hardware not usable, or if you use it, you're not as efficient. So you don't want to go pay $1 billion for a system and end up with 20% or 30% performance improvement. It's not the ideal thing. Then the question would be, maybe another reason to push for use of AI in HPC is that basically the divergence might hinder porting codes for HPC AI. Then you might have to be forced, even if you're not using AI for efficiency or higher fidelity, as much as possible port some of your code to use AI inside the science. I'm not saying use AI like as a complementary or outside your main thing, but actually to be an integral part of your code. It might be the case. I'm not sure if this is right or wrong. And with that, I finish.